Hi, welcome back to the breadboard and another TI Tuesday. And if you're listening, you can hear a weird whirring in the background, giving you a clue of what we're going to look at today. It is the Stepper Motor Boosterpack from TI, and what this is a booster pack to go on top of pretty much any of the LaunchPads, and it hosts the 8711 stepper motor controller with some FETs, which is a SPI based communications device to either the MSP or any of the other TI microcontrollers, or even anybody else's, whether it be Arduino or Raspberry Pi or anything like that. So what we're going to have a look at is a quick tour of what the board is, what's on the board, how you can control it. We'll use a quick and a gear sketch to have a look at it, and we'll see it in operation. So first thing to do is to show you it actually operating. Let's go have a look. Just stopped it running for a moment. I just took the power off of the motor so we can have a quick look at the board. So this is the board. It's actually sitting on an MSP-430 5529 LaunchPad. This is the board here. So you've got two connections for power coming into the board, anything up to close to 50 volts. We'll look at the spec sheets in a minute. You have four connections to go out to a bipolar stepper motor. This is the red, yellow, blue and green wires that you'll see in a moment. Let me zoom out just a little bit. There we go. So you've got the four wires. You have four FETs on board. So we've got 8 FETs, but they're in dual packages. So that gives us two complete H bridges, and we'll have a look at that in the diagram in a moment. Two current sense resistors of 0.05 ohms each, one for each H bridge, and then we have the 8711 stepper motor controller, which is here, and this connects through to the SPI bus and down to the LaunchPad. Now it's also got on it step and direction pins and a few other pins that you can use to control it in its default configuration. But you know, as stepper motors come in all sorts of sizes and voltages and currents and everything else, then you will want to configure it to suit your particular stepper motor, and that's where the SPI bus comes in and allows you to program a whole host of parameters. So let's just zoom this out a little bit and see what I'm driving with it, because it is pretty big considering the size of this. Put my finger there. It's quite small, the FETs and the chip, so you wouldn't think it would be able to drive a huge amount of stuff, but I am actually driving this, which is a fairly large chuck for a 4th axis for a CNC machine. So you've got your stepper motor over here, and it's geared down 6:1 ratio, and then up to the chuck here, which is where you would mount work and everything else that you'd want to do. So let's just power it up again. Okay, so I've written a quick sketch just to rotate it a full revolution, then reverse a full revolution at a 10 milliseconds per step. There's a bit of tape just to help us identify where it's at, and then a quick 2 or 3 milliseconds per step in each direction as well. So in this speed, it takes 12 seconds to do a full rotation of the chuck. And you can see here it's controlling 3 amps. I've actually programmed it for a 3 amp current sense into the stepper motors, and it's quite happily handling it. It's not getting hot on the chip or anything. Even the FETs aren't, because they're working in, right now I've got it working in full step mode. When we look at the specs, you'll see that you can actually program this up to anything up to 256 microsteps, which is quite impressive for a controller. And as you can see, there's not a lot of chips or peripheral components with this, except for the FETs and the current sense resistors. So that's what it's doing, and basically that's all it does. You tell it to step the stepper motor, rotate it in either direction and things like that under software control. So this is just to show you something that can easily be integrated into a CNC machine, a 3D printer, a robot, anything else you would like that involves driving stepper motors. And you can use it to drive little stepper motors like this, alright, just tiny ones, and even smaller, right up to big ones like this. And if you really want to, you can even drive this one. This one's called a NEMA 34. The one that's on here is a NEMA 23. Anyway, let's go look at the schematics of the board and the specs and see what else it can do. So before we look at the schematics, here's a close-up view of the board. The the DRV8711 is one of the standard stepper motor driver chips from TI, and you can see it right here in the middle. It's got quite a few pins on it. Very few extra components are actually required on this board. A couple of LEDs here connected to two of the outputs from the 8711, one to indicate a fault condition and one to indicate a stall condition. These two resistors, as you'll see in a moment in the schematics, are used to measure the current flowing through the coils of the stepper motor. And then we have the 4 FETs. They're pairs of FETs, so they form 2 H bridges, one for each coil of the stepper motor, and then this is the power coming into the board. Large smoothing capacitor just on the power supply, just to add a bit of decoupling. And that is about it. That really is all that is required to talk to this chip. The potentiometer down the bottom left here is actually not used by the chip or anything else, but it is there connected to one of the pins of the booster pack if you wanted to read it and from experimentations and use it to change the speed or something like that of the stepper motor. You could just easily integrate that into your code for experimentation purposes. Anyway, let's go look at the schematics. Okay, so this is the schematic of the board, and as you can see, there is not a lot on it. These are the dual power MOSFETs, they're NEX FETs. The two current sense resistors that I mentioned, there's one of them here, 0.05 ohms, and here's the other one, and they go to 2 input pins of the 8711 chip, and then the GNDB and GNDA are connections that go out to the coils of the stepper motor. And these are the LaunchPad connections. There's the potentiometer that I mentioned. It just comes straight into pin 2, which you could just use as an analog input, and as I said, make it control things. There's the stall and fault indicators coming in for your code to be able to use it. Sleep, clock, reset, step, and direction, they're all control pins going into the 8711, as is SDAT I and SDATO, which is the serial data in and out of the SPI bus. So let's go look at the specifications for the DRV8711, and you'll see how all of these things tie in together. So this is the data sheet for the DRV8711 stepper motor control IC, and I will provide the links to these so that you can grab them yourself. So what's built into this is the ability to do pulse width modulation, microstepping yourself if you wish, or you can use the built-in capabilities of the chip. It can do anything from full steps down to 250 steps per stepper motor turn. So the stepper motor that you were seeing just a moment ago has a 1.8 degrees per step rotation, and there's a 6-to-1 gearing between it and the chuck of the 4th axis that was on there as well. So it actually takes 6 times 200, so 1200 steps to actually make a full rotation of the chuck. I had it running in full step mode in that demonstration I just showed you, but you can program it to get smoother responses by changing values of the registers that are inside the control chip. Now, if you do that, then of course it takes a lot more steps to rotate the motor. A bunch of other programmable parameters on the 8711 as well. For instance, the decay modes, stall detection, where you can tell it how many steps and it actually detects the voltage across the FETs to figure out that it's stalled. You can adjust the current that you're allowing to go into the coils of the stepper motor, and there's a register that allows you to program that. And the idea of that is that a lot of times, as you can see here, a stepper motor controller will have a very high voltage coming into it. In the case of my one, I had 12 volts feeding it, but the stepper motor itself is only actually 3 volts stepper motor, and it's got a 1 ohm coil, and it will take about 3 amps. But I'm feeding it with 12 volts, so how does that happen without blowing anything up? Well, the controller chip actually limits the current, and when it detects that the current has built up to the right amount, it'll actually shut it off. And that's very typical of a lot of higher end stepper motor controllers as well. When you start getting into CNCs and everything else with your stepper motors, you really want to be able to drive them with a lot more torque and power, but still restrict the current to within the operational specifications of the motors, and this controller is able to do that. There's a lot of other programmable parameters in here, and we'll have a quick look at that part in a moment. The 8711 uses external MOSFETs as well. Some controllers you can get have built-in MOSFETs to do their work. This one requires external ones, so you can put as big or as small MOSFETs as you require for the stepper motors that you're going to be using. Alright, here's a nice diagram of the chip. Let me just zoom out a little bit. And what we have here on the left are the interfaces to the microcontroller. So the main two, you got the SPI bus here, you got your fault install indicators going out. You feed it with standard 5 volts for the chip and the interface logic, but that's not the same supply as the volts that are going to go to the motors. Now up the top here, this is an important little thing to take a note of. There's a built-in charge pump capability. When you have high side MOSFETs, N-channel MOSFETs, you need to be able to get the volts on the gate of the MOSFET above the source voltage, otherwise you won't be able to turn it on. And the only way you can do that is to use a charge pump or some other mechanism or a separate supply that is set up to be above that. In this case, the motor controller 8711 supports a charge pump, so the VM, which is the volts to the motor, feeds into the charge pump, and then it elevates a supply voltage for driving the high side FETs properly so that they can turn them fully on. If you look at just one section here, you'll see the high side FET output driving the gate of the FET, and then you've got the motor, and then you've got the low side FETs coming back, and then it's going to go to ground. And here's the sense resistor here that we looked at in the other diagram. This is the 0.05 ohm sense resistor, and you can see that both sides of it go to a differential amplifier and then go and feed into the PWM logic for driving the system. And the same for the other channel. So you've got one motor here and one motor here. Then they're the same way. The supply comes in and it's driven through the FET out to the motor and back in, or it's this side through the FET, through the motor, and down on this side of the FET. So it's a very typical H-bridge, but the common has of both sides of the H-bridge are sharing the same current sense resistor. The torque DAC allows you to also control how much power is going out to the stepper motors by varying it, and these work together to be able to set the current. That's basically just a zoomed in view of what I was just talking to you about. This is actually showing where two of the parameters are going to come into the system. So you've got a programmable gain amplifier here. I'm using it in ×5 mode, and then you've got a torque value that's going into this torque digital to analog converter with a summation point here. Most controllers from Gecko and various other pieces will take you to 1/8 or 1/10. A few go to 1/16, but not too many go down to 256. You do not get more power by using microstepping. What you get is a smoother control of the stepper motor. Here's the diagram I was talking about for the microstepping and how it affects it. So in this first diagram, you've only got 1, 2, 3, 4, 5. So this is probably 8 steps. I don't know if I can see that by zooming in or not. I don't think it's telling me the micro steps. Anyway, as you increase the number of micro steps, then as you can see here, you get a smoother sine wave, because what you're trying to do, it's a magnetic core, it's an inductor, so it doesn't like having changes of current, and if you try to feed it a square wave, it really wouldn't work very well. So ideally you want to feed your stepper motor sine waves, and you would phase them in the standard way that you do drive stepper motors. But by using a sine wave, it's going to be much smoother, and you're going to have much better control of the motor overall. And this is what happens with these 4 diagrams here as you increase the number of steps per pulse. So this bottom one would be effectively 256 microsteps per full step of 1.8 degrees if you were using a 1.8 degree motor, and this top left one here would, for instance, be a 8 microsteps per step. Now the way I was driving this, I was actually feeding it a square wave, so I had full steps. So it would actually be output if I put a scope on, and it would show up as a square wave. Okay, so here we have the registers, and there are 8 registers in the controller chip that you have control over. The first one sets up the mode with the gain and things like that. Then you've got torque, the turn off times, blanking times, decay times, and things like that. So a whole bunch of parameters that allow you to configure the way that the motor is going to be driven. And some of the important ones are, for instance, in the register 0, turning the motor on and off, setting its direction, the stepping between quarter step, 8 up to 256 steps per full motor step. And what the code I'm going to show you does is it always toggles the step pin, but rather than toggle the direction pin, I was simply sending a command to invert the sensing of the direction pin, which saves me having to change this direction pin. It's still a command having to be sent out, so really it doesn't save me anything. I just wanted to demonstrate the fact that you don't have to actually toggle the external pins to the chip. You can actually do everything via the SPI bus if you wanted to. This is setting the current sense. So we have a 50 milliohm resistor, and we have a gain of 5, so whatever the current is going to get magnified by 5. The drive registers, this is for overcurrent protection. So if for some reason you had a short or whatever, it will measure the voltage going across the FETs, and you can set it to be 250 millivolts, 500, 750, or 1 volt. Drive currents for driving the FET gates, and then a status register, which is where you can read back what is happening, because there's only one fault output and one one fault output and one stall output. So if you want to know which channel is in error, then you can actually look in the status register and determine that. So this is where you can set the maximum current for your stepper. So we have 256 times the gain times our sense. That equates to just simply 64 in the case of the design of the board, if I have it programmed with a gain of 5, which I do. So the formula basically becomes 2.75 times torque over 64. And I set the torque for the motor that you saw on the 4th axis to 64 as well, which means that the current basically becomes whatever the volts is, that's the current maximum. So it's 2.75 amps. Now my stepper motor is actually a 3 amp one, but it just was easier just to set it to 2.75 amps for the sake of demonstration. If you're designing your own system, one of the things that TI datasheets always have is some construction guidelines at the end for laying out your boards and things like that. And obviously with things like a stepper motor controller where you've got the FETs on board as well, you're going to have a lot of high current paths that you need to pay attention to. So it's well worth reading those if you're going to be designing your own boards. If all you're going to do is use the booster pack, then of course it's done for you, and that's fine. So let's go look at the FETs that are being used on this board. This is the chip, and as you can see here, we have 2 independent FETs in it, both N channel. They will work up to 60 volts, and when they're fully turned on, they have about a 12.5 milliohm on resistance, which means that they won't be dissipating very much power at all when they're turned on. And the V gate source is only 3 volts, so that's where the FET will start to turn on. So it's easily controllable by 5 volt logic, but as I said, if it's a high side switch, you need to elevate that above the VGA, the source voltage of the FET, which could be 50 volts or maybe typically a 48 volt power supply to drive the stepper motors. So the 5 volt driving to the gate wouldn't do it from the TTL side of the chip. You would have to go up to in excess of the 48 volts by at least 3 or 4 volts, maybe more. You would want to have the charge pump bringing the gate voltage up above the source voltage that might be, say, 48. So that's why they include that in the controller, so that you can actually have those high side switches. It'll handle the 15 amps, but you'd have to make sure that the chip is fully turned on where it's only got about 12 milliohms, so it's got nowhere near the 2 watts of dissipation in that situation. So going back to the stepper motor controller and the main board here, that pretty much covers everything that this can do. Now the one nice thing is you can buy this from directly from Texas Instruments, or you can get it from RS Components. You can get it from Element 14 or Farnell's. And the price of this, let me just have a look what it currently says on TI's website, is $25. Now, even if you're not using a LaunchPad, you can just desolder these pins, or you could put it onto a strip board with 3 other ones. So you could have 4 of these on a strip board, have them hooked up via the I2C bus, and bring out the lines to an Arduino, to a Raspberry Pi, or anything you like. Very, very easily, because it's using standard interfacing logic. You don't have to do anything special for it. So it will be very easy to build your own controller, whether it be for a robot or something else. It really, the imagination is your limitation, or your imagination. Before I go, I didn't show you the code that I wrote, and I will provide this as well on the site. I'll provide a link to it as soon as I've got it posted somewhere that you can access. So this is set up for the MSP-430G2 as I said. So very simple, include the SPI drivers, a little bit of information about hardware serial, not that we're using it in this particular case. Define the pins that are being used by parts of the controller, setting up a few registers for step and direction, initializing some of the standard I/O. And if you're used to Arduino programming or LaunchPad and a gear programming, then you'll know exactly what this is doing. Setting up the serial port so we can just output any information if we want. And when we start up, I do output the parameters to the serial port, so you could see what they're set to. We call and initialize and get current registers. Get current registers outputs the registers out to the serial port, so you can see what I've set. The initialize it comes down here, and it basically just outputs 1, 2, 3, 4, 5, 6, 7 of the registers and sets up their values. So I've written here what it's doing. So we're enabling the motor, we're setting it the indexing on every step, not that we're using that. We're setting it to full stepping, not microstepping. Internal stall detection with gain of 5 and 850 nanoseconds of dead time. We're setting it for 100 microseconds and 2.75 amps of current to the motors, 31 microseconds of off time, and we're telling it here to bypass the internal indexer. That's where you want to use a pin from the outside of the chip for stepping versus sending a SPI command to say do another step. And then a few other parameters, just configuring various other aspects of the wave shaping and current detection and things like that. And that's pretty much it. And then the get current registers just reads them in and just prints them out to the serial port. And I have a loop here, just very simple. I've got a rotate one direction for 200 times 6 or 1200 steps with a 10 millisecond delay per step, which means it will take about 12 seconds for a rotation, and then go backwards again, and then do the same thing again with about a 3 millisecond delay per step, which obviously rotates it much quicker. Rotate it back again, wait a second, then just going to repeat that. Now, anybody that's used to programming in Energear and stuff will definitely know that, this shows you how to make it turn and how far to turn, and it will be a simple case of adding the extra control logic to respond to commands from the serial port or something else to make this work. And I will be doing more of that when I get more into specifically putting videos up on stepper motor control and motion control for my CNC that I built specifically for the purposes of teaching you all about steppers and everything. But I'm not going to deal with that here. What we're really looking at here is how the 8711 and the Stepper Motor Booster Pack works and how easy it is to drive it. And you can see here, this is not very much code, and I'm able to get that stepper motor driving very, very easily through the SPI bus. In fact, there's no real libraries except for the SPI bus library that is being used here. So this code could be taken and almost, you'd have to map to different pins on an Arduino or a Raspberry Pi, but you could take this basic code and port it easily across to any other microcontroller, and it would still work quite happily. So that's it. I hope you enjoyed that, and I will see you on the next TI Tuesday. Bye.